Okay, welcome to the lab. We'll get started in just a minute or so. So we'll get started in just a minute or so here. And again, we're officially starting the next experiment, which should be the equilibrium complex metal ion. And then we're just going to kind of go over when we get started here, just sort of an introduction to the experiment. And then, like usual, he could go off and kind of work on it if you like, and I'll hang out. If you want to come back and ask some questions and stuff like that. Okay, so why don't we maybe get started here? So, officially, again, a couple reminders. I think let's just try to summarize everything that we got going on in terms of the lab. I believe your first lab report should be due today. Yes, so hopefully you've uploaded that. And that was the one we actually did in person, I think, if I'm not mistaken. So that was our triiodide experiment. So that I think is due today. I think next week, if I'm not mistaken, the kinetics activity will be due next week. And so make sure, obviously, you're going through that one. And again, a reminder, I believe off the top of my head, the kinetics activity was pre-lab, post-lab, and a data section that had sample calculations, if I'm not mistaken. And again, that one is coming up as well. That was sort of that Excel exercise, I think, sort of, where you had to make all those graphs and stuff like that. Any questions on any of that stuff before we talk about the new one here? Okay, so the new one is equilibrium of a complex metal ion. The module should just open there at 11:30. So if you go to Canvas when we're done here, or whenever you want to go there, and you'll be able to see an entire module that's made up pretty much of this experiment alone. So everything in that module is for this experiment. What you'll first see, I think, is a page that describes a couple of things. It has some links to the sort of lab pages that you would have in your lab manual. So when you click on that page, it'll also have some of the pages where you could click and see like the pre-lab questions, I think, the post-lab questions, the introduction to the experiment and stuff like that. On that page as well, it will have it will also have the procedure written out and maybe the modified procedure for how you're going to do this experiment on there. In that procedure, there'll also be several things that you'll need to click on, which will be some photos of actual of the experiment actually being done. And you may have to look into some of these photos and record some information, things like temperatures and obviously observations and stuff like that. You'll also find in that module a link to sort of they made a like notebook sort of page that you could kind of fill out and submit as your carbon pages for this experiment. So you might want to click around first before you start writing things and stuff. But I believe there's sort of a page, one of the files there or pages there is like a submission of sort of like the stuff that you would put in your carbon pages and stuff like that. You'll also find a file up there as well that is a data file. And so each of you were sort of assigned some different data to use for this experiment. So if you're collaborating with others, they may have different data that they were assigned. So there's just sort of randomly assigned, obviously. But you'll have a data set that is also a PDF file that you can download and open. It will have some absorbance values and stuff like that that you can use for this experiment, obviously, to do the graphs and the calculations. Now, in addition, you'll also find a couple of other files up there. One's an SP file, I believe, and one's a CSV file. And these are like the files that so we did like the kinetics experiment using the Spec, the Pasco Spec spectrophotometer. And if you remember, you had a couple of options in terms of how you could save that. You could save it as sort of a Pasco file, which I think is the SP file that you'll see up there. And you can either save it as a CSV, which you'll also see up there as well. So I think they made both of those files, which are the two files that you would have been able to sort of save when you were doing the experiment like that as well. Again, the CSV file would be one where if you wanted to take it to Excel and do the work in Excel, you could do it in Excel. The file that's labeled SP at the end of it is the file that you would use to use the Pasco software. So in the procedure that they made, as you go through it, there'll be a spot where it says you should go to Pasco, I think is the name of it, if I'm getting it right, and download their little software. And that's the same software that we use for the kinetics experiment. It's the one that has like all the colors, looks like a rainbow type of thing. And you can download that for free. And you can use the SP file and have it do all the graphs and that type of stuff for you. Or if you choose to, you can again use the CSV file and go to Excel and do the graphs through there. Again, sort of your choice, just like it would be in class, whichever way you want to do it. And maybe easier to use their program, but you could use Excel using that CSV file. Any questions on sort of that part of it? And this will make sense, obviously, when you get to when you look at the module and stuff like that. Okay, so let's actually talk about the experiment and sort of what's going on. There's really two parts to this experiment. The first part is the Le Chatelier's principle part. So the first part is really the Le Chatelier's. Badly spelled there. So the very first part of the experiment, like you would have done in class, and for this experiment, we're really looking at this reaction here. It's really iron 3 plus some thiocyanate going to come together to form a complex ion, which is over here. So this is the equilibrium we're looking at throughout pretty much the entire experiment here. And again, we can write our equilibrium constant, which is our products, which would be our complex ion here, divided by our reactants. And in the first part of the experiment, what you would have done in the Le Chatelier's principle part is really set up this equilibrium. And you would have made a bunch of test tubes that had this equilibrium going on. By the way, the guy on the right there is a dark, really dark kind of red color, kind of really dark red. On the left there, the iron 3 is kind of orangey and that type of color. So it kind of goes from orange color to a really dark red if it's shifted to the right. And again, you could use that to help you kind of determine colors and which way it would have shifted. Again, this more of a dark red, more of a kind of orangey yellow type color. And again, if you did something to this equilibrium, once you set up this equilibrium, what you would do when you're going through that first part was, for example, add, say, iron 3 nitrate. And if you added iron 3 nitrate to this, for example, it might be something you're adding. Iron 3 nitrate really is a source of two things. It's a source of iron 3 and nitrate. Yeah. So just like in Le Chatelier's principle, if we're adding something, in this particular case, it would be like adding more iron 3. So as we were talking about today, if you added more iron 3, it would expect to shift the equilibrium to the right. And visually what you would see is a change in color. So again, it would go from maybe that yellow orangey color to a really dark red color because you basically added more iron 3. Now you're going to be adding different reagents. And again, there will be some pictures of each of those things. It's kind of after those reagents were added and before, obviously. And what you want to look for in this case is evidence of it shifting either to the right or to the left. And you're going to be able to determine that by the change of color that occurs, or maybe the no change of color that occurs based on what you're adding. And then you're going to need to figure out, based on what you added, what was causing it to shift to the right and what was causing maybe to shift to the left. Remember, this is adding. We can also talk about, like we did in class, about if you want to remove something, you might add something to it that maybe made it precipitate. Also, maybe, maybe not in this case, but could have made water. That's again another way that you could remove something. So when you think about the reagents, like what we have here, and you think about what you're adding, you want to think about what that reagent is a source of. And just like I did there. And if you see that part of that reagent is actually in the equation, then it probably means you're adding that thing. If you see that you added something that nothing is in the equation, so nothing's in that equation, but the two sources of whatever you added was not there, then probably what's happening is one of those guys is able to react with something that's in there. So for example, I won't do these examples too many because I'll probably do the right ones. So I'm just going to do randomly, like if I added A, B to this, yeah, this is a source of A and B. And if I look at A and B and it's not anybody in this reaction, but I did see something occur, what that must mean is either A or B is reacting with somebody in this reaction and perhaps making a precipitate and removing something. So those are things you want to look for when you're doing the Le Chatelier's principle part. Either you're going to be adding something that's there, and then obviously it will shift away, or you may be adding something that reacts with somebody in that equation, and it may be removing something, which would shift it to the side of what you removed it from. And again, the way you're going to visually be able to determine that is from these pictures by looking at obviously color changes and which way the color sort of changed. Again, if it got really more of a darker red, that means it shifted to the right. Not so much dark red, kind of got lighter and maybe heading towards orangey yellow, it would have shifted to the left. Any questions on sort of the first part of the experiment, which is the Chatelier's principle? Obviously, you should be making observations of what you see in those pictures. And like I said, if you look at that, there's a file, I think, to kind of use as notebook pages if you want. So you could use that if you like. Any questions on sort of the first part here? So really the first part is a lot of what we were talking about at the end of that chapter, the Le Chatelier's principle and shifting to the left, shifting to the right. If I'm not mistaken, I believe in the pre-lab questions, you're supposed to predict, yes? So you're supposed to make some predictions. So if you haven't done the pre-lab questions, obviously you should do those first before you look at all the experiments and the pictures. Otherwise, if you do the predictions afterwards, they're not much predictions. They're just what you saw. Yeah, so I believe you're supposed to do some of the predictions beforehand. So make sure you kind of do them in the right order. That way you can see if you were right or wrong. Any questions on Le Chatelier's principle part? Okay, so the next part of the experiment is actually one where we're going to be looking at the same reaction. So I'm just going to flip the page here. And we're looking at the same equilibrium. So again, we have our iron 3 reacting with our thiocyanate, making our complex ion. eraser here. And 2 plus. And again, same equilibrium constant as what we had on the other slide there. Okay. So in the second part of the experiment, in part 2, I'll call it, I don't know if that really is the part number there, but after the Le Chatelier's principle, the goal of this part of the experiment is for you to actually determine the value of K. So you're actually going to determine what the value of K would be in this part of the experiment and get an actual value for it. And you're going to actually do it at 2 different temperatures. So kind of a cold temperature and a hot temperature. Remember, as we talked about in that first chapter, that the equilibrium constant, the value of the equilibrium constant, is not affected by anything. So that what that means is that you can start with different amounts of the reactants, different amounts of the products. They will eventually all come to equilibrium and end up at the same ratio and end up with the same value for equilibrium. That's why it's called an equilibrium constant. The one exception to that is temperature. Temperature is the only thing that will affect the actual value of the K, or the equilibrium constant. That's because as you increase the temperature, as you decrease the temperature, when this thing comes to equilibrium, it may come to equilibrium at a different ratio as it would. So, for example, at room temperature, the K value may be 20. Perhaps you increase the temperature to a higher temperature, the value would, say, just go up to 120, for example. Now, what that means, though, is if you keep the temperature at that higher temperature and you add different amounts of reactants and products, it will still maintain the same K until you again change the temperature. So temperature is the only thing that really will affect the value of K. But if you keep the temperature at a specific value, the K value will remain constant. So what we're looking at is when you eventually do all these calculations and you figure out the K value for the 2 different temperatures, you should have a different value of K for your cold and hot temperature. But within your cold temperature, that value of K should be about the same because it's a constant. And within your hot temperature for your different test tubes that you do, the value of K should be about the same. But when you compare the cold temperature to the hot temperature in terms of the value of K, they will be different. Any questions on that? So in order to do that, what you're essentially going to do is we're going to use that Spec, kind of like Spec 20 from Pasco, kind of like what we used before, and that kinetics experiment. And we're going to, first part of this, called part 1 of this one, you're going to make a set of standard solutions to make a calibration curve. So basically, we're going to set up these guys in such a way that we're going to have a set of standards of known concentration of our product. Now, in order to do this, the first part of the experiment, where you're making your standard curve, was set up in a way that we had a bunch of our thiocyanate. So we essentially have a whole bunch of it is, right? So just like in basic stoichiometry, when you do limiting reagent problems, it is the limiting reagent that determines how much product you would make. So the way that they set up the first part of this experiment here, when we're doing the equilibrium part, is they set it up in such a way that the iron was the limiting reagent. So if you know how much iron you started with, which you will know from the table, you could figure out how much product you would make because it was set up in this direction. So that's something very specific for what's happening in the part of the experiment where you're going to be making your standard graph. Any questions on that? So because of the way it was set up, you will eventually have, once you do the first part of this experiment here, you will have the concentration of your product based on the limiting reagent. And you will also have some absorbance values for, I forget how many test tubes. I can go with 6, maybe 5, maybe more. But I think it's about 6 test tubes. So you'll have a bunch of absorbance values, numbers that correspond to concentrations in each of those test tubes. And what you're going to make is a constant of the ends. And again, it will give points. You get best straight line. Yours will be better because it'll be cuter. And so equals x plus b. And this is all based on b times d. C concentration and b friend here. So b is up here and come from your mind, come from your right, but here's constant. Which is over concentration and goes here. So the whole purpose of this very first part of the experiment, when we're doing part 2 here, trying to figure out the equilibrium constant value, the whole purpose of it for this first part is to make a Beer's plot. And the whole purpose is really just to get the slope, to get the Beer's constant. Now, when you do that, if my memory serves me correctly, should be a pretty big number in terms of Beer's constant, if I'm not mistaken. So it shouldn't be a small number. If I'm not wrong here, I think it should be a pretty big number when you do the graph. Any questions on the first part? So that's essentially the first part of obviously calculating K, is to make the standard curve. Again, as you go through the module there on that page, there'll be different pictures at different steps that will allow you to make some observations. This is also where you can download that the Pasco Spec software. Again, that's free, just like you might have already downloaded it from the first experiment. And again, I think when you download it, it's got like the P in the middle and it's like rainbowy, it'll look like. And this is where you can use and the absorbance standard curve to make. You will need to calculate the concentration for each of the absorbance. So again, you can also use label very. So you have a couple options as to how to make the graph. You could either use, again, a software that we used for the first one, or I believe there's a file that you can use for Excel as well. And again, in the procedure there, if so, again, don't follow the procedure perhaps that's written in your lab manual, even though it's going to be very similar to what you read online. Follow the ones online. Again, online, it will have the pictures that you need to look at, and it will kind of give you the little clue like, hey, go download this file and use this software, and kind of tell you what to do. Any questions up to that point there? So at this point, you will have part 1 done for the equilibrium calculation. The second part of this experiment here, after you make your standard curve, is we are again still going to be looking at, so part 2 of calculating K. We're still going to be looking at the same reaction throughout the entire experiment. And obviously, we're still looking at our same K. Now, in this part of the experiment, you're also going to make a bunch of test tubes, in theory. That is going to be cold and hot in terms of its temperature. And again, I want to say maybe there's 5 or 6 test tubes. They're actually the same test tubes. The only difference is you're going to take these test tubes and basically put it into a water bath, a warm water bath. You're going to heat them up before you actually do the experiment part. So in this part of the experiment, unlike the part where we did the Beer's Law graph, we didn't make any of these reactants sort of excess or limiting. We didn't really force the reaction to go all the way to the product side. So here we didn't do that same thing as we did with the Beer's constant, where we forced it essentially to all go to the product side. So what we have in this situation is you're going to need to do eventually an ice table, and you're going to do an ice table like we talked about in lecture for each of the. So for each individual test tube, you actually will have to do an ice table. We'll talk about a way you could do it a little quicker perhaps than by hand, but we'll talk about how you need to do the calculation by hand. So for each of these test tubes that you start with, you will have an initial concentration of iron 3 and thiocyanate. Remember that when you're figuring out the initial concentrations of the experiment, you want the concentration of these guys in the test tube, which means you need to do much like you did before, a little V2 action, since you are doing some dilution as you're adding nitric acid, you're adding other stuff to the test tube. So you want the concentrations of these guys in the actual test tube. So we'll require you to do that calculation, kind of similar to, I think, the concentration sort of activity we did at the very, very beginning of the semester. So you want to make sure that you don't use the concentration that's sort of on the bottle. You need to use the concentration for each of these test tubes in this part and all the other parts as well. That's actually in your test tube, which would require you to use the dilution equation. Any questions on that? So using the dilution equation and getting the correct initial values of this, so I'm just going to go number initial and number initial here. That would be your molarity basically, right, of this guy. Your molarity and your molarity. We will assume that we're starting with 0 of our products in this part. The change here would be minus x, and plus x. At equilibrium, you would have your initial concentration minus x, and have x here. So this is essentially what the ice table would look like for each of the individual test tubes that you have. Now, the goal here is to actually find the equilibrium value constant and the value of it. So normally, right, we take that and stick it into our equation here. X and our initial minus X and our initial minus X, and we would take it and use our number. But in this case, we don't know what this is. So that is the goal, is to really find what the value is. So we need a way to actually figure out what X is. And this is where your standard graph will come into play from the first part. And again, you're going to have your slope, right, which equals Beer's constant. So again, we did for both the hot and the cold. So for the cold as well, you'll have all these absorbance values for these different test tubes. You'll have absorbance values for each of those. So what you would then need to do is use Beer's law. And in this case, what you would have for each test tube that's hot and cold is you would have the absorbance value. You would have Beer's constant for part 1 that you did. And you could solve for C. C would equal A divided by B. And that will give you the concentration of that test tube for our product at equilibrium. Yes. Any questions on that? So here's where we're going to use the Beer's constant that you got from your graph from part 1. You're also going to use the absorbance values for each of these test tubes in the cold and hot to figure out the concentration of your product at equilibrium. Any questions on that up until this point? This is important because if we go back to our table, change the color here. If we go back to our table, we will see that at equilibrium, if I can find my pen, there it is. At equilibrium, X is equal to the concentration of our product at equilibrium, which means this number that you get here, take the long way, is going to be your X value. And the nice thing about that is this X and this X and this X, they are all the same, which means this X value, and it's going to allow you to then get the actual number for each of those. You'll figure out each input, and there. Any questions on that? So we're going to use the standard curve there from part 1 of this to figure out Beer's constant. You then will use the individual absorbance values for each of those test tubes at the cold and hot temperature. And you will use Beer's constant to turn that into a concentration. That concentration will equal X in your ice table for each of the test tubes. And that will allow you to get the equilibrium concentration of everybody in that reaction, and then get the actual equilibrium constant for everybody in that reaction. Any questions on any part of that? So here's where I said you could do this one of 2 ways. If you like, you could do an ice table for each individual one and then put the numbers in. Or if you're good with Excel or use Excel properly, you could have Excel pretty much calculate your K value for each of those. So if you put in, for example, a column that's the initial concentration of iron 3 for each of those test tubes, a column that's the initial concentrations of the thiocyanate for each of those test tubes, a column that has your Beer's constant in it, and a couple of columns with your absorbance values. You can have pretty much Excel do all the calculations for you, and then also do the calculation for K for you by putting it into Excel. So since you have to calculate K for all those test tubes, you may want to have Excel kind of help you out and do the calculation with it. I would recommend that you double check Excel just to make sure it's doing the right calculation. But you can have Excel pretty much calculate all the K values and everything for you by doing it. Yeah, so essentially, just so we're all clear, let me just summarize sort of what you need to do here for this one. So again, I apologize. I don't remember off the top of my head, but I think it's somewhere about 5. So again, you're going to have about 5 test tubes that were done in sort of room temperature, a cold temperature. Those same 5 test tubes were then going to be heated up at a hot temperature, and you will end up with absorbance values for 5 temperatures, 5 cold temperatures, for example, and absorbance values for those same 5 at the hot temperature. You essentially have to do this process for each test tube individually. Yeah. Which means when you're said and done, if you did have 5 test tubes, you would have 5 K values for each of them, one for each. You would also have 5 K values, for example, for each of those in the hot temperature. And that means that at total, you need to calculate something like 10-ish or so K values, depending on how many total test tubes there were. So you could technically do each one by hand, like I just kind of did on the board there with the actual numbers, or you can put into Excel. Usually what you'll need to do is have a column of your initial iron concentrations for each of those test tubes. You'll need the initial concentrations of the thiocyanate for each of them. You'll need to put into like a column or a cell Beer's constant. You will also need to calculate the absorbance values. So you'll need a column with the absorbance values as well. And then you essentially can have Excel calculate your concentrations from everybody, because you would need just the absorbance values and Beer's constant for each of those test tubes. So you could put in a formula like equals, whatever cell divided by whatever cell, basically, into Excel. And then once it calculates those concentrations, you basically can put a formula into Excel that is basically the equilibrium expression, and you can have Excel calculate K for you as well. So you need to kind of put into Excel each of those values in columns, and then you need to use formulas, and you could have Excel actually calculate both the concentration using Beer's constant, and you could also have it calculate K as well. But you would have to input obviously the numbers into Excel, or copy them over into the proper columns, and then do some formulas. Other questions on that? So when you're all done with this part of the experiment, like I said, you should have a K value for each individual test tube for all the cold measurements, and a K value for each of the individual test tubes for the hot measurements. You then will probably be asked through the data analysis to calculate like average K values and so forth, and you can compare them. Any questions on any part of that experiment there? Okay, so the lab report will be a formal lab report, so we'll do a whole one on this one, and then probably for the next couple we won't do so much of a formal one, but we'll do one more formal one just to make sure we did at least a couple this semester, I suppose. So this will be pre-lab, post-lab questions. You'll need a typed introduction, data section with sample calculations, and a results and discussion section as well. You will need to show at least one ice table worked out and part of those sample calculations for your lab report with actual numbers. Obviously, you don't need to work out all 10 of them or whatever, but you do need to show sort of at least one all the way through. I imagine if you show one all the way through, that probably will take care of all the sample calculations you probably would have to show for the most part. But that should probably take care of most of it. Obviously, you'll also need to include in your data section, in this case, your graph, your standard curve that's been properly labeled, that shows your equation and all that good stuff. So you'll have to show that kind of stuff as well. Any questions on any part of the experiment? Again, tentatively, it's going to be due, I think, the 23rd of April. So that should give you hopefully enough time. If not, I may adjust it, but excuse me. As of now, it's something like the 23rd, I think. Any questions on anything? That should, I think, cover most of it. Yeah, I think, again, you want to make sure you go through, there should still be the data analysis part of the experiment. So you want to make sure you go and calculate whatever they tell you to calculate. But my guess is, since you did a whole bunch of them, something like an average value would be a good idea to calculate for the hot temperature to cold temperature. And that way in your report, you can maybe just talk about the average K value for the cold was this, the average K value for the hot was this. And you can maybe talk about, Are they close to each other? Are they very different because of temperature change? You know, you can kind of talk about those type of things. But you do want to make sure you still go through sort of the data analysis section. It should sort of walk you through the calculations like I just kind of did sloppily here on the board. Um, but it will kind of tell you what to calculate. And just like normal, anything that it says to calculate, you know, within the data analysis section should be calculated, and obviously probably should end up in a table that you make of yourself of proper values, you know. So remember that in the report, I don't necessarily want you to type in the data analysis part or anything like that. What I want you to do is just to make sure that you did all those calculations, and then you should take those values and put it into a table that you make, a nice organized table and stuff like that, or two tables or however many tables you need. Any other questions on this experiment? Okay, so like I said, it should be up there, the module, and if I clicked everything correctly, again, some people, different people in the class will get some different data values to use. So it should show up for you. One that says like data set 1, data set 2, or something like that. So you'll have some different values and stuff like that. But make sure that you do go through, obviously, what they made in terms of the procedure that's on that very first thing that you could click on, and make sure you read it really carefully and do the observations and stuff. I probably would try to click through everything a little bit, just to kind of look at everything and make sure you sort of understand where things are and what you need. And then, you know, as you work through it, you can do that. A lot of the stuff you'll be able to download those files and kind of open them and kind of reference them and stuff like that. Any questions on anything else? Okay, so at this point, I'm pretty much done talking, I think. I know, keep the applause to yourself. I will still be hanging out for, you know, another couple hours, I think. So I won't be talking or anything, but I will be here. So if you do have questions, you can feel free to, if you want to hop back in or whatever and ask the questions, you could type it and I'll get back to you in terms of answering them. I will, once I'm done with all this, post this up on. Okay, I'm gonna double check everything just to make sure everything is hopefully open, and you should be able to get to it. But I will make this lab video. I'll post it up online with our other stuff. That way, in case you need to kind of reference what we just were talking about, you'll be able to do so as well. Okay. Any other questions? Oops. Okay, so if you're good, you're welcome to hop off and you know, go work on that, and you can come back and ask questions or hang out. And I may have to go fix a couple of things. I'm going to go double check some things right now.